Hello, and welcome to week 2 of instrumentation and measurement in ME397. This week we're focusing on the basics of digital data acquisition. For a transducer, in your assignment we're going to be using a load cell, which allows us to measure a force on an object. And we're going to be reading that through a digital multimeter, which is our digital device. In the process, we're going to have to learn about how digital information is transmitted and stored. We're going to have to learn about how voltages are measured in an analog device, and we'd also like to know about the error in the device. We'll estimate it using measurement uncertainty analysis. This will connect nicely with what we discussed in the course syllabus. Scroll down to the What You'll Learn section. Notice there's the common measurement systems that are of importance to a mechanical engineer. Well, forces are pretty important, so load cell will allow us to practice that. The idea of transducers, which will allow us to convert energy from an observable physical phenomenon, like a force, into an analog electrical signal, like a voltage. And digital data acquisition, whereby we convert that analog voltage into a discrete digital information, in this case display it on the screen of a multimeter. And we'll touch on uncertainty analysis as well. We'll hold off on the LabVIEW programming language until a little bit later in the course. First, we'll gain some confidence and some abilities with the other subjects. Instrumentation and measurement always begins with what we want to measure. Usually there's some sort of physical phenomenon that we'd like to capture: temperature, pressure, flow, displacement, in our case force. And to measure that electronically, we need some sort of electronic transducer. Now, Omega provides a nice definition. A transducer is a device that converts some sort of physical energy into an electrical voltage or current signal for transmission. And if the device is linear, as we talked about in the last lecture, then what we need is knowledge of the static sensitivity, the slope, that allows us to convert the measured electronic signal, voltage or current, into the desired physical measurement. For a load cell, that's force. I'll show you here an example from the Omega website of an S-beam load cell. And we have some sort of a connecting point there and there. We can apply tension or compression. And mechanically, this S-beam will imperceptibly deform. And they're actually load cells, strain gauges actually, applied to the structure that are producing a voltage output through a Wheatstone bridge. And don't worry, we'll talk about that a lot more when we spend a couple weeks on strain gauges. Once the transducer has converted that into a voltage signal, we later on, after wiring, connect that to a data acquisition system or a measurement system, in our case a digital multimeter. Let's talk a little bit about the end product. The data acquisition board or the measurement system, in our case the digital multimeter, its job is to display a reading from the measurement. Now that's a digital device, and as such it's discrete in time and amplitude. For each period of time you have a certain value of measurement, a discrete data point. And that information is stored using a binary system. Computers are binary systems. It's a base 2 number. And a binary digit, or a special definition called a bit, is the smallest piece you can have possible. The computer stores that in its memory as a 1 or a 0, a switch, on or off. Those are the only two possibilities. And how we store more complex information is by connecting lots of bits. So we can collect bits to express numerical information in a word. And a typical 8-bit word is called a byte. So when you have a 1 gigabyte memory stick, that's 1 billion bytes possible. And then the physical location on an electronic device, whether that would be, for instance, RAM, memory, or a hard drive, That's the register. As an example, you've probably noticed that our ability to store information increases in both speed and quantity. It seems exponentially every year. As an example, on the course website, I have a link here to breakthrough at IBM, where researchers were able to store 1 bit, a 1 or a 0, on as small as 12 atoms of matter. I have a picture up here from one of the links, a New York Times article. So if you can store 12 atoms for a bit, a 0 or 1, just think on a larger scale memory disk or memory stick, just how many bits and bytes and words we can store on that kind of information. So how does this work? Well, with computer language, we use different combinations of bits to represent our decimal base 10 number systems. So I have a table here. You could have, for instance, a 2-bit word, and with 2 bits, 2 0 or 1s, we can have 4 possible combinations, and those 4 possible combinations could stand for our base 10 numbers 0, 1, 2, or 3. For instance, I could have a 0 and a 0. I could have a 0 and a 1. I could have a 1 and a 0. I could have a 1 and a 1. So all told, that's 2 squared equals 4 possible combinations. And each one of those could be stored as the 0, 1, 2, or 3. Well, that's a really simple case. Computers now are easily 64-bit. We'll just look at 16-bit. 16 bits, that's 2 to the 16, equaling 65,536 combinations. So you can just imagine how big of a range of integers we can store on a 64-bit system. To go back and forth, to convert binary to decimal, there are a couple ways, and I'll just talk about this one, straight binary code. Now let's say for our binary code we have I don't know, we'll say 0, 1, 0, and 1. Well, we'll number them starting from here. This is bit 0, and this is bit 1. This is bit 2, and this then is bit 3. Okay, so 4 bits starting with 0. And what we do is, for instance, this is a 0. So I'll take 0, and then I'm going to multiply it by 2. Remember, base 2 number. This is bit 3 raised to the 3rd power. The second bit is a 1. So I'm going to take 1 multiplied by power 2 raised to the 2nd power. My first bit is a 0, so I have 0 multiplied by 2 to the 1st power, and then my 0 bit is a 1, so I have 1 multiplied by 2 to the 0 power. And I add all of these results together. So I'll take that, add it to this result, then add it to this result, and then add it to this result. Sorry if my handwriting looks like that of a first grader. I'm doing the best I can. Okay, well, let's look how this works out. I have 2 to the 0 power, which is a 1, multiplied by 1. So that gives me 1. Here I have 2 to the 1 power, which is 2, but it's times 0, so I have a 0. Here I have 2 squared, which is 4, and that 4 is multiplied by 1, so I have 4. And then here I have 2 cubed, which is 2 times 2 is 4, times 2 is 8. 8 times 0 is 0. So add all that up together, and my base 10 number is actually 5. Okay. Note how how bit 3 influences the number the most. If that bit was stored as a 1, I would have added 8 to the answer. Whereas my 0 bit, 2 to the 0 power is 1, it just adds a 1 or a 0 to the number. This has the least possible outcome, and so we call it the least significant bit. And then this one has the most influence on the outcome, so we call it the most significant bit. And as you might realize, the least significant bit then is sort of the resolution at which we're able to store information, the smallest possible increment, which has an impact on our error estimation, uncertainty calculation a little bit later. Okay, so now we know a little bit about how digital information is stored on an electronic device like a computer or a multimeter with memory. Now we need to talk about how that digital information coming out of the data acquisition is transferred to that device in the first place. So we transmit binary code using switches that alter the voltage. So we have usually a voltage coming across the line or a wire. And we let a high voltage represent bit 1, or 1 on a bit, and then we let a low voltage be measured or interpreted as a 0 for the bit. And usually we know that there's going to be noise on the line, so to account for error, instead of specifying an exact voltage that must be met, we define some sort of a range to give us some error tolerance. Let's draw a picture, sort of shows us how that works. I'll have a horizontal axis, and I'll also have a vertical axis. And let's see, I'll call my vertical axis E for voltage, electromagnetic potential, and I'll call my horizontal axis T for time, since we're transmitting the signal over time. And what we end up with is a bunch of voltage pulses. So let's say I have, here's a voltage pulse, and let's say it's coming across as, let's say that's coming across as 5 volts. There we go, 5 volts, and then here's 0 volts at the bottom. Well, this pulse is some duration of time delta t, and it's a high voltage, so it will be represented as bit 1 stored by the device. Then we have another pulse of the same time duration. In this case, it's, well, I guess you could say the absence of a pulse. That's interpreted as a 0. And then we have another pulse. In this case, it's a high voltage. It's of duration delta t, and so it's interpreted as a 1. And so in this way we have high-low voltage pulses that are interpreted then as 1s and 0s. And this is actually called, this 0 to 5 volt line method is called transistor to transistor logic. That's TTL. Transistor to transistor logic. And if it's transmitted just one line, we call that serial. So for serial, we're talking about 1 bit at a time. And if we want to increase the density of the signal, the amount of data we transfer over time, well, there are 2 ways of doing that. One is to reduce the time span for your pulses. Now, if you get that too small, you're going to have possible error spikes that are interpreted incorrectly as 0 and 1s, so there's a limit. But that's one way. Another way is to add multiple wires, and then you're sending across multiple information, like 8 bits at a time over 8 wires. And that method is actually called parallel transmission. So that would be multiple bits at a time. Okay, you have these two options. And in the past, I might be showing my age here, if you wanted to transmit a lot of information, for instance to a printer, you had to use a parallel printer cable. That was because serial transmission was so slow. But with the fidelity of computer transmission technology, we're able to use pretty much serial communication for everything. And the ubiquitous way of doing that is with the USB, Universal Serial Bus Interface. So it's sending out these voltage pulses at very small time increments. Continuing to work our way backwards, we've discussed using a computer for digital data storage. And we've talked about transmission of digital information over wires using serial or parallel transmission, transistor to transistor logic. We've been talking about the digital domain, numbers stored as bits, zeros and ones, combinations then standing for our base 10 number system. Okay, so voltage measurements are analog. How do you interface digital equipment to devices that are analog? Analog by nature is continuous in amplitude and time. Digital is discrete. So we're measuring, for instance, forces via a load cell. Well, as the load changes with time, that's going to be sent by a transducer as some sort of continuously varying voltage, an analog signal. And we somehow have to get that into digital information that can then be transferred and stored on a computer. Well, the device for the job is the analog to digital converter. And the process by which it does that is called quantization. The process of quantization, of turning an analog voltage into discrete digital information, is a lot like using a ruler to make a length measurement. And I'll use a picture here to show you what I mean. Let's draw a crude rectangle to represent our ruler. Okay, so that's our analog to digital conversion device. And let's say there's some sort of length that I want to measure, or a voltage in this case. And so I have some sort of range of voltages I can break this into. So let's say this is 0 volts. Let's say this is, I don't know, 4 volts. And then this would be 1 volt. Trying to break this into even increments, 2 volts. That's a pretty good job. Okay, so 0, 1, 2, 3, 4 volts. And then, here's my, we'll call this my unknown voltage that we wish to measure. Okay, so my ruler is sent into increments of volts, and then on the digital side, I can represent that by a certain combination, certain resolution on the ruler. So if the ruler is in 1 volt increments, well, the best I can do with the measurement is to say it's somewhere between 3 or 4 volts. With a ruler, if you have a 1/16 of an inch as your finest resolution on the ruler, then the best we can do is measure the length down to a 1/16 of an inch. So on the analog side, we have our full-scale voltage range, something like 0 to 4 volts. On the digital side, we can represent that as 2 to the m binary numbers. So maybe 0, 0, 0, 1, 1, 0, 1, 1, for instance. And then combining the two allows us to determine the resolution of the analog to digital device. Let's take this example a little bit deeper and bring in some of our knowledge of circuits from our electrical engineering classes. Don't worry, won't be too much. Okay, so taking that same ruler analogy for a DAC card, turning analog information to digital information, we have at the base a op-amp serving as a voltage comparator. Okay, and the number of comparators we have in this case helps us determine how many bits we can use for our words. And in this case we have 2-bit logic, so a word for us is going to be 2 bits, and that limits us then on the combinations, the numbers we can store. So in this case we can have a combination of 0, 0. We can have a combination of 0, 1. We can have a combination of 1, 0. And we can have a combination of 1, 1. That's not pi, that's 1, 1. Okay? On the analog side, then we have some sort of voltage range over which we are measuring an unknown voltage. Well, let's say in this example we're going to say our voltage, FSR is the terminology we're using. Oops, FSR is equal to 4 volts. Okay, that's our full-scale range over which we're expecting to measure some unknown voltage. It's got to fall in between that. Well, if I take a resistor ladder, make a voltage divider circuit, okay, more practice from circuits, well, my reference voltage is going to be 4 volts. And I have 4 identical resistors, so here I'm going to have 3 volts. Here at this juncture I'm going to have 2 volts. Here at this juncture I'm going to have 1 volt. And then at my ground I'm going to have 0 volts. Okay? That's as coarse as my gradations are going to be. And then here I have my unknown input voltage. My unknown input voltage, and so I'll call that EN. And that's going to be equal to 2.5 volts. Just to make an example here. So my input voltage that's unknown to my DAC card is 2.5 volts, and it's going to look for it in a range from 0 to 4 volts. Well, let's look at this comparator. It's going to take the input voltage and compare it with 1 volt. Okay, well, it's going to be greater than that, so we'll say that trips. Then we have our second comparator, op-amp, which is going to be comparing the input voltage to a 2 volt reference signal. It's going to be greater than that, so it passes that one. And we look at our third comparator, and it's comparing the input voltage to the reference at 3 volts, and now this one does not compare, it's less than. So in this case we know that the signal is somewhere between the 2 volt reference and the 3 volt reference. That's all we know, right? That's the resolution of the device, somewhere between these two. So we come here, and our 4 volt range is split between these 4 possible combinations. So the signal 0, 0 could be between 0 and 1 volt. The binary 0, 1 would represent anything between 1 and 2 volts. The 1, 0 would represent anything between 2 and 3 volts. And then the 1, 1 would represent anything between 3 and 4 volts. Okay, and that's the best we can do. And this is where we get that equation. Q, our resolution for the device, is equal to E FSR, full scale range, divided by the combinations of our device. It's a 2 raised to the m, the number bit system we have. In this case we have a 2-bit system. So we have 4 minus 0 volts divided by 2 raised to the 2 power, or we have a resolution of 1 volt. That's the best we can do in this case. And this specific type of arrangement is called a parallel converter. Again, excuse my writing. Parallel converter. The parallel converter, or flash converter, is not the only way to configure a to D converter system. I have that listed down here at the bottom. It happens to be the fastest, but it's also the costliest. It's the costliest because it requires 2 to the m minus 1 separate op amps serving as voltage comparators. The benefit is that the conversion then only takes 1 clock count per combination of op amps. In our example, it was pretty simple. It was a 2-bit system, so 4 minus 1, we needed 3 op amps. The common DAC cards, though, you're looking at 12, 14, 16 bits. So you're needing over, 65,000 different op amps for your 16-bit system. And that drives up the cost a little bit. The second fastest and second expensive is the successive approximation A to D converter, and it's actually using a trial and error approach to figure out what the voltage is. And this is very similar to what you did in ME397 numerical methods when you used the bisection algorithm. So I'll write that here. The bisection algorithm in ME397 for root finding. So let's say we set our unknown voltage range to 0 to 4 volts, and then we do a comparison with our 1 op amp, and it falls within that range. Okay, now we divide that by 2 and test, is it between 0 and 2 volts? No. Well, then we know from that test that the voltage must be between 2 and 4 volts, and we keep on halving and doing our comparison. The downside is that it requires 1 clock tick every time we do that. For an example, a 12-bit A to D system with a 1 megahertz speed computer clock needs then 12 microseconds per conversion. And that would add up. However, computers are getting so fast, we can really usually get along with this, except for the highest or more complicated needs. The slowest and cheapest is then the ramp converter. So it's used for high accuracy and also low levels, voltage levels, less than 1 millivolt. It's inexpensive but slow, and it's actually based upon the time it takes to charge a capacitor until its output voltage matches an input voltage. Those are the 3 common kinds. So let's talk about common types of error that are associated with analog to digital converters. The first we'll look at is quantization error, and that's the difference between the actual analog input analog value and then what the computer is storing as the binary output. And that's directly related to our quantization calculation. So Q is equal to our full-scale voltage range. In this example, we've got 4 minus 0 volts, and we have a 2-bit system. And that gives us 1 volt for a quantization error, the resolution of our device, in other words. Let's look at this graphically. So we'll draw a y-axis here. That's going to be binary output, and then we'll draw an x-axis that's going to be our voltage input. So there's volts, and there's binary. Okay, and our binary could be 0, 0. It could be, let's see, I need to draw some good even gradations here. So there's 0, 1, 1, 0, and 1, 1. And then I need to draw that same width here. Maybe I'm getting better at this. So we have 0 volts, 1 volt, 2 volts, 3 volts, 4 volts, and 5 volts. Okay. Ideally, we would have a one-to-one correspondence between these guys. So let's see here. 1-to-1 is going to look something like this. There we go. Okay, and we'll label this as our ideal comparison or relationship. But in reality, we have the discrete nature of the digital world. And so what that looks like is, let's see. So any voltage above 3 volts is going to be recorded as 1, 1 on binary. And now discretely, anything between 2 and 3 volts is going to be stored as 1, 0 in binary. Anything between 1 and 2 volts is going to be stored as 0, 1, and anything between 0 to 1 volts is going to be stored as 0, 0. So in reality, there's our quantization issue. And this is called, let's see if I can draw it there. There we are. Right? That's our 1 volt quantization problem. An AD converter actually makes this symmetric. So I can shift this scale, and if I shift it, I end up with, I could put 0 here, 1 here, 2 here, 3 here, 4 here. So there's 4, 3, 2, 1, and 0 volts. Okay. And this is typically a AD converter makes this symmetric. Okay, and thus then the error for due to quantization is plus or minus 1/2 of the quantization. So I'll write this way. The error associated with quantization is equal to plus or minus 1/2 the quantization error. Okay, you can connect this to last week when we were talking about basic overall instrument error. The first thing we wanted to know was the resolution of the device, and then we said that the error due to resolution was plus or minus 1/2 of the device resolution. Well, the analog to digital converter is another type of device in the instrument, and so its quantization error is going to be felt, its resolution is plus or minus 1/2 Q. You should be aware that in the literature, the spec sheets that come with a lot of devices, they'll speak in terms of signal-to-noise ratio, which is another way to express quantization error. It's the ratio of the signal power, E squared over R, to the power resolved by quantization. So that's E squared over R divided by 2 to the M, and it's given in decibels. So the signal-to-noise ratio in decibels would be represented as 20 times the log of 2 raised to the M power. So for an example, let's say we have a full-scale voltage range of 10 volts. Okay. Then if I look at bits, remember that's M in my calculation. Let's look at a 2-bit system. And just for the heck of it, let's look at a more realistic 16-bit system. Well, I can calculate my quantization error. Remember, that's in volts. So for a 10 volt full scale range, a 2-bit system is going to give me a quantization error of 2.5 volts. And a 16-bit data acquisition card is going to give me a quantization error of 0.00, come here, 0.15 volts. Okay, so 0.15 millivolts. And sometimes you don't want to write all the decimals, so instead we can write it in a signal-to-noise ratio in decibels. Well, using my calculation here, then my signal-to-noise ratio would be 12 decibels. And then for a 16-bit card, my signal-to-noise ratio is be calculated as 96 decibels. So the higher the signal-to-noise ratio, right, signal over noise, the higher it gets, the better off you are, the higher bits you have in your quantization. A second type of error in A to D cards is saturation error. And that's the fact that, remember, we have to set a voltage range. So there's a minimum and maximum analog voltage limit. And the difference between the input voltage and then what that limit is the resulting error. Let's draw this graphically. So we'll have our binary again in the y-axis, and we'll have our voltage on the x-axis. There's our voltage. There's a binary. And remember, we had a binary 0, 0 at the bottom here. There's 0, 1. There's 1, 0. And then there's 1, 1. Then over here on voltages, let's see if I can get this. 0 volts, 1 volt, 2 volt, 3 volt, and 4 volts. Okay. Well, remember, if I look at my quantization, then I'll draw it like this, coming in horizontally, and then at 3 volts, 1, 1, my next quantization is down to 2 volts. My next quantization is down to 1 volt, and then I have anything less than that. Okay? Well, here's my problem. Okay, let's say I'm putting in a 6 volt signal. Well, the maximum it's going to show up as is somewhere between 3 and 4 volts. So I can't even recognize what that number is. In other words, my DAC card is saturated in the signal. So anything above that range is going to be saturated. And that works on the low scale as well. I could have a negative voltage coming in, for instance, but the lowest thing I can write is, or resolve, is 0 volts, somewhere between 0 and 1. So you can have saturation on the low end as well as the high end. And third source of error in A to D measurements is conversion error. So analog to digital problems, error sources such as settling time, signal noise, temperature effects as extraneous variables, also power fluctuations. All those things can combine to yield errors such as hysteresis, linearity, zero drift, and repeatability that we talked about last week. All those things affect the A to D process, and so the manufacturer will then include those in specifying an accuracy for the system. So you have resolution and then also other sources of error together that must be combined. Finally, we recognize, in terms of error estimation, uncertainty analysis, that each component of the apparatus or the instrument in its totality can have its own sources of systematic error. These are then combined together, as we saw last week, using the root sum square method. So looking at my diagram here, we have basically two devices. We have a transducer, and then we have a data acquisition board or measurement system. Our transducer in this case is a load cell plus actually a power supply. Okay, and our data acquisition system is for the week going to be a digital multimeter. In this case, our physical phenomenon is going to be a force. That force is turned by the load cell into a voltage, which is then passed by wiring into the data acquisition card. And that's how we get our voltage. Okay. Now, there is some air across the wiring. That's usually random noise, which is not systematic air. Remember from last week we quantified that as random or precision air. We'll talk about that later in the course. Right now we're just looking at systematic. Okay, so how do I combine both air sources? Well, remember from last week, the digital multimeter might have a resolution error, it might have hysteresis, repeatability, linearity. So we would combine all of those using the root sum square method to get the total uncertainty of the digital multimeter. The load cell. Okay, we would look at the specification sheets from the manufacturer to get the linearity, repeatability, hysteresis, all those types of possible error sources that have been calibrated by the manufacturer, and we combine those using the root sum square method to get the uncertainty of the load cell. And then finally we can combine all of those together using the root sum square method to end up with the uncertainty of the force measurement. Okay, so let's do that. Remember, we want the overall instrument error. Okay, my overall instrument error is the same thing as saying the systematic uncertainty in the force that I wish to measure. And that's then going to be equal to the root sum square of the systematic error in the load cell squared plus the systematic error in the digital multimeter. And again, this is actually plus or minus. Okay, it's as simple as that. We've got to remember, however, in the process that units might be different, and we need to use unit conversions using our sensitivities as necessary to make sure everything's in the proper units that we expect, forces. And when you come into lab on Thursday, we will put this into practice using a load cell and a digital multimeter to prepare you for your first big assignment.